Ladies and gentlemen, welcome to my presentation on the ideal factory for filling liquids. Ideal factory is a high claim, and yet it makes sense to think about in order to then implement the best possibility in reality. It is mainly about pharmaceutical products, but in principle, it also applies to other high-quality liquid products where efficiency and cleanliness are important. My name is Christoph Bohn, and I'm Director of Rommelag Pharma Service. I have had the opportunity to be part of the project team for several pharmaceutical production buildings in the Rommelag Group and as a consultant at a lot of projects for customers. The topics I would like to talk about today are basics for pharmaceutical factory, sterile products, the royal class of pharmaceutical products, about filling technologies for sterile products, the ideal factory for filling liquid pharmaceutical products, and a comparison of factory layouts for aseptic filling technologies. At first, I want to go to the basics for a pharmaceutical factory. For the filling of pharmaceutical products, there are very detailed specifications that have the character of law and are audited by the state. But it is not defined in detail. It is the task of the pharmaceutical company to transfer these regulations in a functional concept. They are defined, for example, in the European Gmp Guideline, in the FDA guidelines and CFR regulations, Pharmaceutical Inspection Conventions, WHO. What are Gmp requirements? A logical flow, adequate space, a structured personnel, material and waste flow, clean room concept to prevent contamination, to avoid intersections, and a good cleanability and easy maintenance access. I would like to briefly quote some key passages from important regulations, starting with the European Gmp Guideline. It's the same in the WHO guideline. There it is stated in the principles: premises and equipment must be located, designed, constructed, adapted, and maintained so to suit the operations to be carried out. Their layout and design must aim to minimize the risk of errors and permit effective cleaning and maintenance. And one sentence from the WHO guideline: premises should be designed to ensure the logical flow of materials and personnel. It's in nearly the same way stated in the 21 CFR part 211.42 about design and construction features. Any building or buildings used in the manufacturing process, packaging or holding of a drug product shall be of suitable size, construction and location to facilitate cleaning, maintenance and proper operations. But there are not only Gmp requirements. A company can only function if it is also economically successful. Therefore, besides the Gmp aspects, economic factors are also essential. Exceptions prove the rule. In extreme situations, this can also be undermined, as we have now experienced in the pandemic, but this is not a sustainable concept. In some examples we have already seen that also economic requirements are very important for a successful production. The next section deals with sterile products, the top class of pharmaceutical liquid products. When we talk about liquid pharmaceuticals, they are often sterile. If possible, there has to be a terminal heat treatment after filling, but often this is not possible. So the product has to be filled aseptically. Let's have a look on some examples. We have large volume parenterals. They are mostly terminally sterilized. Then we have small volume parenterals or injectables. They are often terminally sterilized, but also there are a lot of cases, a lot of products, because they are unstable. They are often sterile, also could be with a low bioburden. Ophthalmica also are mostly sterile. ointment, enemas and gels, eye care, nose care, contact lens cleaning. It depends from the product itself. It has to be sterile, or this also could be filled with a low buyer burden. But we can see it's really necessary for a lot of pharmaceutical products, liquid pharmaceutical products, that they have to be sterile with a heat treatment or through aseptic filling. Filling of sterile liquid products are defined and regulated in mostly annexes or separate guidelines. For Europe in the Annex 1, for the FDA in the FDA Aseptic Guideline, and WHO has also an Annex 6 where it is described how to fill sterile products, and also other national regulations are there depending on the country where these products are used. If you have a look in the Annex 1 for European GMP efforts, there is a special focus on minimizing the risk of microbiological contamination and of particulate and pyrogen contamination, skill training and attitudes of the personnel involved. Clean areas should be maintained to an appropriate cleanliness standard and supplied with air, which has passed through filters of an appropriate efficiency, airlocks for personnel and for equipment and materials, and various operations of component preparation, product preparation, and filling should be carried out in separate areas within the clean area. Also, the guideline from an organization, from the ISPE, is quite interesting, related to layouts for ideal factory. There, a short summary: layout should prevent product cross-contamination, environmental contamination, and address product operator. One-way flow around open processes is an approach to address cross-contamination prevention. And process storage should be provided, and the logical flow of product components in order to prevent mix-ups. An important principle behind these regulations is a shell model, which also can be called the aseptic core principle. I will use this as the central model. The ideal factory can also be derived from this. The innermost core is aseptic filling. If products are terminally sterilized, in many cases, one of the outer shells is sufficient for filling of these products. But for aseptic filling, it always means compliance with Class A or Class 100 conditions in the filling area. In the ISO terminology, this is not quite so easy to represent, as this is designed also for cleanroom applications in general, for microelectronic, etc. And it's really important to realize that the difference between the individual shells is not simply a half of the specifications. It's a dimensional leap in each case, at least if you look at the number of particles. Also, you can see this in the description for the US market. There we have the class 100,000, class D. Class C means class 10,000, class 1,000, class B, and class 100, the class A. And that's the number of particles, 0.5 micrometer particles. And there you can see it's not only half of the specification, it's really a dimensional leap. And technically, this means to reach this dimensional leap, it means more air treatment, more air exchange rates, and because of this, a higher investment and higher operating costs. And that's really important to understand also from the economical side to create the ideal factory. Let's have a look on the filling technologies, sterile products. We have the conventional filling in a class A area with a class B background. I will come to more details in the next slides. Then we have advanced aseptic technologies, the restricted area barrier system, or filling in isolator technology, or filling with blow-fill seal technology. These three filling technologies are called advanced aseptic technologies. This is, for example, stated in the USP. Why is this stated in this way? Let's start with the conventional filling. In the so-called conventional filling, the filling machine is placed in a room, and conventionally, because this was the starting point for aseptic filling in the past, and this is also used today in a lot of aseptic productions. The characteristic of the conventional filling is that an operator directly intervenes in the filling line. To reduce the risk, the filling line is placed normally directly under an HEPA filter, class A quality. Often the critical area in the room is separated with a curtain, and the background has to be a class B environment. You can see this also on this shell model I put here, and the operator is working in the class A area and in the class B area in the background. For the factory, the consequence is that all cleanroom zones has to be installed. And between each cleanroom class, a personal material lock is necessary, except between class B and A. Let's come to the RAPS technology. This means restricted area barrier system. In this system, the operator is outside the filling machine and can only intervene in the production via gloves. This is a significant additional protection for the aseptic process. For cleaning and disinfection, the RAP system has to be opened. Today, normally a RAP system is located in a class C area, so the operator not needs to wear a class AB gowning. With the new Annex 1, this could change because there it is stated that a RAP system for aseptic processing should be placed in a class B environment. Inside the RAP system, we have, again, the class A aseptic filling zone. Let's talk about isolator technology. In an isolator system, the operator is outside the filling machine and can only intervene in the production via gloves. But additionally to the RAP system, the isolator is a closed system with an own air handling system, and it's also normally decontaminated with vaporized hydrogen peroxide. This is an additional safety margin also compared to the RAPS technology. Today, an isolator system could be located in a class D area. In Europe, in the US, it has to be placed in a class 10,000 area. So the operator also not needs to wear a class AB gowning, and the operator is working in this class D or in the class 10,000 background and only has this indirect access to the isolator. Last but not least, let's talk about the third advanced aseptic technology, the blow-fill seal technology. The very interesting characteristic for the blow-fill seal process is that the containers are also created in this process. This is done with the extrusion of pharma-grade plastic resin, mostly PE or PP. The main advantage is to have newly created containers. Also, this has some challenge, but this is another topic. But a newly created containers is very safe, respective to contaminations. Since 30 years, this technology is mentioned in the relevant regulatory documents for sterile production. According to these regulations, the blow-fill seal system has to be placed in a class D area for filling of terminally sterilized products, for aseptic filling in a class C environment. Because of the high automation grade, this is normally only necessary for an operator to work in the class C area during the start or stop phase. During the production, the operator can run the machine from outside the cleanroom area, for example, in a controlled, not classified area. And the class A area is part of the machine itself. It's implemented in the blow-fill seal machine itself. Blow-fill seal technology is often not so well known. Some more information for this reason for this technology. There are two main principles: the shuttle type machine with a mold shuttling between parison and filling position. There are several types available for ampules, for large volumes, for several production capacities. And also there is a rotary type principle. In this case, it's a closed process during the filling. The filling mandrels are located inside the parison. Please feel free to look for more information at the Rommelag site or the Rommelag virtual booth, or get in contact with us. The blow-fill seal technology is used since the 1970s for pharmaceutical filling, and also it's worldwide accepted for aseptic and terminally sterilized liquid products, and also in the most important regulations, it's also stated how to use this blow-fill seal technology for sterile filling. So let's come to the ideal for filling sterile liquid pharmaceutical products. The ideal factory is very simple. A very clear and straight unidirectional production flow. The personnel with restricted access to the areas of operation with shortest ways how they can reach their area for their working operations. That's the ideal factory. If you use the GMP criteria with such an ideal structure, the main risks are reduced. We have a logical flow for material, product, and personnel. There's a reduced risk of contamination. There are no intersections. The critical areas are minimized, and there are reduced human interventions with such an ideal layout. If you have a look from the economical side, also we see the advantages, the shortest ways possible. Then also minimize critical areas. That means because critical areas always are expensive from investment and running costs. Also, such an ideal layout reduces the costs for investment and for the operation. And also it allows a high automation rate. If you have a closer look, the following main process steps has to be implemented. We have a storage area for incoming goods. It's normally controlled, not classified. Then there is a solution preparation, mostly class C. Then there's a filling area, depending on the filling technology, class A, B, C, D. Then there's, if a terminal sterilized product is produced, there is a sterilization necessary, and also a packaging process. And this process is after the filling, after the container is closed, is normally also done in a controlled, not classified area. And at last, the warehouse for the finished goods. That are the principal process steps in such an ideal production flow. So after defining the ideal factory for liquid filling, it is time to compare the discussed filling technologies and the consequences for the ideal factory. When we talk about the filling, it is this is the part in the middle of the production process. It's like the heart of the process itself, is the highest risk of contamination because their bulk is filled into several containers, and there it's the highest risk of a contamination. In this example, it looks very small because in this example, blow-fill seal technology is used, which has the advantage of a small footprint. And as mentioned before, the critical aseptic process is part of the machine itself. This could be much more space if other technologies like isolator or rub systems are used. And additionally, much more personal material locks if it is a conventional filling. The other areas could be nearly the same size. In this table, we compare the clean room size and class for the several filling technologies. The numbers come from a typical layout, but can differ for specific projects. And you can find huge differences in the clean room size and spaces. Let's start with the conventional filling. The controlled, not classified area, that's the packaging area in this process, is for all technologies nearly the same. For class D and C, we only have small spaces because that's more material and personal locks. But then we have the aseptic core, which is very large area because the filling machine and the conventional filling is in this class A and class B area located. So there are a lot of cubic meters which has to be controlled and are necessary to run this open conventional filling process. So if you have a look on the isolator, there we can see we have more of this low level class D or C environment, depends from the philosophy of the company. There the isolator is located, and the isolator itself has the internal class A area around 15 cubic meter in a typical filling machine with several steps. For the RAP system, we can see the shift more to a higher cleanroom class because it's only a restricted area, a restricted access. It's not completely closed. So we have a higher cleanroom class, but nearly the same size like the isolator filling concept. So if you have a look on the blow fill seal filling technology, there we have for aseptic filling a class C area. The space is much smaller because of the smaller footprint of the machine itself than for isolator or RAP system. And I think most important, the very small space for the critical space for filling, for the filling process, it's only a fraction of a cubic meter. So that's really the main difference. And these are the advantages also from investment side, but also from the contamination risk side, because it's a very small area which is critical at a blow fill seal concept. If you compare how the GMP criteria are fulfilled, we see the following picture. The logical flow, it's depending on the layout. That's not a function of the filling machine itself normally. And then for the risk prevention, we have no risk prevention for the conventional filling because we have this direct impact. The isolator, we have a complete closed system. It's a very good risk prevention. For the restricted access, it's good, but lower than for isolator. And for blow fill seal, also we have an automated process without possible intervention of the operator. So it's also a very high risk prevention. If you have to focus on the minimized critical area, conventional filling, we need this room with class AB. Isolator, we have a reduced space compared to conventional filling. It's the same for the RAP system, but we only have this fraction of the space in the blow fill seal machine. Also, this is really a high advantage to reduce the risk of contamination. Also, if you have a look on the human intervention and the necessary, there's the full risk for conventional filling. Isolator, there's no direct intervention. For the RAPs, it's restricted. And for blow fill seal, again, also there is no human intervention necessary in the process itself. If you compare how the economical criteria are fulfilled, we see the following picture. The shortest ways, that's again more on the layout of the factory itself. If you have a look on the critical areas, we have this complete AB area for conventional filling, the reduced area for this advanced aseptic technology isolator and RAPs, but nearly the same. But this very small footprint and this very, very small critical area in the blow fill seal machine, which also reduces the costs for investment and the running costs for the factory itself. We have a high automation rate that could be done for all technologies. Also for blow fill seal, we have the automated production of the containers, and I think that's also an advantage. Also, this is an advantage, the dependence on preform containers. There is no dependency at blow fill seal technology, and also this makes it very flexible, also not to store preform containers only. This plastic resin has to be brought into this machine. So let's have a very close look on the layout. That's the layout for conventional filling. There we have this locks which are necessary for material and personnel. Then we have a quite large area for the installation of the machine itself in the under class A conditions and the surrounding class B area, and then the secondary packaging mostly in controlled, not classified. And the operator is working inside the critical area itself. To compare this with a blow-fill seal installation, we can see here several machine types, also different in the footprint. So for an ampule filling machine, for example, it's a very small footprint inside the class C area. The critical area class A is integrated in the machine itself. So there is no additional class A area in the clean room necessary. It's a part of the machine itself. So I call this the triangle of success. To increase the GMP quality, to reduce the risk, it's always increasing the costs and the investment. And so often also increasing regulations has an influence on the costs of the product. But is there a way to be successful and superior in production costs? I think that's the reason a good layout is necessary, intelligent layout, a good decision for the filling technology, which is the best for the product, and then also quality by design. Then also this increasing regulations could be fulfilled, and also efficient and economically successful production is possible. Let's summarize. The ideal factory for filling liquids needs a logical flow, adequate space, structured personal material waste flow, minimal critical areas, minimal human interventions, and a robust and automated filling technology. Hopefully, I covered some points which have been interesting for you. If you are interested in further details, I'm available now for a discussion, and I will be happy to answer your questions.